Yes, so I've started the recording of this session. So now you please come out with your queries. If no such personal query was received by me, which I thought that should be shared here. Yeah, Harsh,
Sir, please explain question number 5 of quiz 2D.
quiz 2. Now I have to look into the quiz. Can you
Yes, sir, I am sharing the screenshot.
yeah, that would be best. Yeah, quizzes, if you have doubts you should ask, because sometimes it might so happen that uh, by like when I was setting the quiz, I did not have all the things in my mind and maybe I have put the wrong answer there. So you should always clarify it for your own understanding. Let me check. Which of the following statements is always true for a matrix with independent row vectors? Okay, the row vectors are independent. Note, trivial null space means that null space consists of only zero vector. Okay, it has a trivial null space if rows are more than columns. This was a thing that I said. Yeah, so there are less number of columns, more number of rows, and all the rows are independent. This is what we are saying. Now,
Sir,
rows
what
being
conclusions can we make from independent row vectors?
yeah, that is a thing. So that is one that is the first thing that you should ask actually. What conclusion can you make from independent row vectors? The conclusion you like in the purview of what we had discussed in all this course, actually there is nothing you can conclude from independent row vectors. So even if the rows are independent, your columns might not be independent. Okay, your columns might not be independent even if your rows are independent. So that is the thing. And while setting this question, I actually had some example in mind, which right now I am not able to come up with some example. Let me see. Yes, like if you have make one column 0 na, and keep the other elements in such a way that the rows become independent, but since one column is already 0, you have already lost a rank. Okay, so you have lost a rank there. So since you have lost a rank, your null space will not be trivial in that case, and this is the first option. So it is important to keep in mind this particular idea, that independence of rows does not mean independence of columns. And in the discussions that we had partaken in the purview of our course, we were interested in independence of columns, only columns. Okay, so
Sir,
yeah.
but if the number of rows is more than number of columns, like the example you stated, like if we make one column 0, so
Hmm.
then too like number of rows are more, so we will always be able to make they will not always be like, if the rows are independent, like more number of rows are independent, then columns will always be independent. We will always be able to like.
No, it is not so. It is not so. So the example I cited is actually, so suppose there are 5 rows, okay, and suppose there are 5 rows and 3 columns. Let's take this. Okay, I have come up with an example. Let's take 5 rows and 3 columns. Now, one column, the first column, you make all the elements 1. In the second column, you make all the elements 2. in the third column you make arbitrary elements in such a way that none of the columns are if you take arbitrary elements without repeating any of the elements, then all the rows will be independent. So you think about this example once more. The first column is 1, all ones. The second column is all the same quantity, suppose 2. The third column you place your entries in such a way that none of the entries repeat anytime. So if that is the situation, all the rows will be independent of each other. No, all the rows will not be independent actually. All the rows will not be independent.
So that is what I'm saying, that we'll never be able to come with an example in
And
which
when we have more number of rows, yes, then Urjita's mic is not muted. Yeah. So yes. So when we have when we are crossing the third row, then from the fourth row onwards we will have we will not have independent rows. Yes. So then this question is framed in this way: with independent row vectors, so in any case, actually the first statement is in conflict. So if the rows are more than the columns and the columns are not independent, then the rows will also be not independent. And actually if the rows are more than the number of columns, the rows will not be independent. And the question started with which of the following statements is true for a matrix with independent row vectors. So the first statement does not even stand, because if you have rows more than columns, then the rows will not be independent even if the columns are independent. Even if all the columns are independent, then also the rows will fail to become independent, because in this situation after 3 number of rows, the fourth row will obviously be some combination of the previous 3 rows. Then the next statement is it has a non-trivial null space if rows are more than columns. It has so if there are rows are more than number of columns, then obviously actually you are not able to the rows can be dependent now, but you are not able to comment anything on the independence of the columns. So that is the main thing actually you should take from here. So you are not able to comment anything on the independence of columns by only knowing whether the rows are independent or not. It has trivial null space if rows are less than columns. If rows are less than columns, now you have a definite actually answer, that if the rows are less than the columns, then some of your columns will become dependent. If the rows are less than the number of columns, then some of your columns will become dependent on other columns. In that case, there will be non-trivial null space. So trivial null space will cease to exist. It will be non-trivial null space. So the fourth option will be correct here. It has non-trivial null space if rows are less than columns. That's last two are talking about if rows are equal to columns. If rows are equal to columns, then you can have independent rows, but your columns can be dependent also. So in this case, actually, you think about that example. Suppose you have a 4 cross 4 matrix, and you have independent, you have uh, 3 of the columns to be same. You can take the 4th column with elements different to each other, and they will be they will become dependent, right? Or they will remain independent. I thought that they will be independent, but they will also become dependent in that case.
If rows are independent, then how can columns be
Yeah,
dependent?
yeah.
If they are equal, if the number of rows and
Hmm.
columns are
When they're equal, yeah. Yes, so I think I had not thought very carefully in this case. Yes. So when the rows are equal, when the rows are independent, the columns will also be independent if they are equal in number. Yes, this has to be the case, because the row rank and column rank will be same for the square matrix. So in this case, you will have a trivial null space. So this answer should be right. So you will have a trivial null space if rows are equal to columns. If rows are less than columns, then you will have a non-trivial null space. And if rows are more than columns, if rows are more than columns, then the rows will become dependent actually. But you will not be able to confer anything about the independence of the columns. So you will not be able to conclude anything about the null space, whether it will be trivial or non-trivial. So in summary, Harsh has raised a very important question here. There is something wrong in this question. It is not absolutely correct. I guess I had not given the correct answer in among the last two. So if I remember correctly, so I perhaps had not given the correct answer among the last two options. So this is important, and so let's summarize what is happening here. So when the number of rows are more than the number of columns, then the rows will not be independent. They can never be independent. Okay. However, even with that fact that they will not be independent, what about the columns? We don't know anything about the columns, whether they are independent or whether there is dependency among the columns. So with the information that rows are more than columns, we will not be able to conclude that. So in that case, there is no conclusion about the null space being trivial or not. When they are equal, then if the rows are independent, the columns will also be independent. Hence, it will be trivial null space. And when the rows are less than the columns, then of course there are dependent columns. When rows are less than columns, of course there are dependent columns, and hence there will be non-trivial null space. That would be the answer here. Harsh, any more question here regarding this?
No, sir, got it.
Okay, there were some other hands were getting raised and they were lowered eventually. So if there are other questions, then please raise your hand or something related to it. If you are still not confused, or whether if I have given some wrong statement somewhere, please point out that. Yeah, Inzamam.
Sir, I have doubt in quiz number 2F, question number 1.
Quiz number 2, question number 1. Okay, I need to open up quizzes, it seems. Quiz number 2. Let me see.
So I have the doubt in the same question and the previous one. In the case when the columns were less than the number of rows, so in that case, why are we saying that it can't be it can't give a non-trivial solution? in
Why
which
are
the
we
rows
saying?
are in which the rows are more than the columns. Let's suppose we have a particular matrix with only one row with some values. In that case, we can obtain a particular solution which gives a non-trivial solution.
But
Only
is it okay? You have more number of columns, only one row, and you will have some vector, some non-trivial solution will be there, that this is 0.
only in the case of square matrix we can arrive at a trivial solution. In any other case, we will have a non-trivial solution. Let's suppose we have a particular square matrix and we start removing the rows or columns from that matrix. Let's suppose we are doing that. From that, we can consider that whatever the resultant matrix should be, they would have some dependent rows or columns always. Either there would be some dependent rows or some independent columns. With that, we can always say that whenever we obtain a rectangular matrix, it will always have a non-trivial solution.
Rectangular is fine, but if you have, okay, so you are saying that there's flat
Non-square
matrix and tall matrix. So if it is flat matrix, then of course there will be non-trivial solution. But what about the tall matrix? So the example you gave was also for a flat matrix where you considered a single row. It is a flat matrix, so of course there will be
we
non-trivial
can take
solution.
the transpose of that particular matrix, and the particular solution won't matter much. The transpose does not change the nature of the.
Yeah. Sure,
So
right.
yeah.
So the
So
transpose, the solution which is for the row, whatever the vector comes out for the transpose, no,
But number of the rank plus that nullity plus rank
no.
should be equal to column. So it cannot be that if there is a tall matrix, when number of rows are greater than columns and all columns are independent, then how can we have
You can't have, yeah, you can't actually have. See, if you make the transpose, Shivam, for the, so you have only a one single row, right? Now you make a transpose, and now you say that this, what is to be multiplied with this, so that this becomes 0. So you can only multiply 0 with it in order to make it 0. You can't have any other vector coming there from the same space. Isn't it so, Shivam?
Yeah, I'm thinking about it.
Okay, so I guess about square matrix and flat matrix we are sure. So for tall matrices, I will pull up the whiteboard and try to see in some examples. Let us do. Before that, let us go into that query Injama was having, which is the quiz number.
Sir, 2F, question number 1.
Quiz number.
2F.
Sorry. 2.
F.
2F. Quiz number 2F. That is a quite a far away quiz. Quiz number 2F, question number 1.
Yes,
Which,
sir, I was not able to understand what this question want to say.
okay. When we apply a matrix A to a vector X in a state space, it inadvertently gets shifted from its original direction. This is a question, right?
Yes, sir. Yes,
Yeah.
sir.
So what the question is saying, that whenever you apply a matrix A to a vector in a vector space, it inadvertently gets shifted from its original direction. But this means that it will always get shifted from its original direction whenever
But
you
sir,
apply a matrix.
But sir, if it is an eigenvector,
Yeah, so the answer is false. So the correct answer is false here.
but sir, inadvertently I've searched the meaning, sir, in unintentionally.
Hmm? What?
So what is the meaning of inadvertently?
Inadvertently means always. So you can say it always, no matter what. Okay.
Okay, sir.
Sir,
Huh.
please use some easy words so that there is no
Actually, sir,
I
confusion and
thought
we
that
actually,
can.
inadvertently is an easy word. If you don't know, if you just simply can Google it.
sir,
It
I
is
Google it.
very simple
It was
word.
showing that unintentionally. It was showing in Google.
Unintentionally.
Yes, sir.
No. Inadvertent means it is supposed it will do like that no matter what condition. Raman. Raman.
Yes, sir.
Yeah.
I have a doubt in quiz 2D question number 6.
2D. Let me go there. 2D. Question number. Question number.
Question number sir, 6, sir.
How many distinct outputs we are getting from an SPR is given by how many distinct outputs we are getting is given by the number of rows of the C matrix, the number of independent columns of the C matrix, both of the above. So you are getting y equals to Cx, right? That is the output. So as many you have independent columns, that will be those many distinct outputs you will get. Other outputs will maybe combination of those distinct outputs. So we are talking about distinct outputs, that means independent outputs which are not, which are completely like maybe if I had used the word independent outputs you would have understood better, but it means the same thing. Did it answer your question?
Yes, sir. I misunderstood the question.
Okay, no problem.
So,
Sarah. Yeah.
yes, sir. So,
Hmm.
does that mean we cannot conclude the nature of output with the number of rows? Like, we cannot comment on it, or is it always true? I did not understand.
See what you are trying to see. You are trying to see the range space of C matrix. So because y equals to Cx, so you are, Cx means you are trying to see where you are taking your x from your state space, where you are taking your x. So what is the dimension of that space? So whatever is the dimension of that space, that many distinct outputs you will be able to get. So if so you have to check the, you have to check, basically you have to check the column rank of C. So you check the number of independent columns of C. That would be the, that would be the dimension of that space, that the dimension of the output space, that would be the distinct outputs. So any other output will always be a combination of those distinct outputs. Rahul. Raval.
I have a doubt. Sir, I have a doubt in quiz 2F, fifth question.
Which question?
Fifth problem.
Sorry.
Fifth, fifth problem, sir.
Fifth problem, quiz 2F.
Yes, sir.
5. Suppose it is observed from certain parts of the state space, the system moves towards the origin for an LTI system. Then from certain parts, not all parts, okay. So all eigenvalues of the system are negative, you cannot comment on that. The system may move, may eventually move away from the origin, that is also true. It may eventually move. So now it is moving towards the origin. it may eventually move away from the origin. This can be true if there are other modes which are which tend to move it away. Okay, if the system reaches the origin, eventually it will remain there. That is also true. Suppose you are able to reach the origin, then you will be there, because unless you are disturbed, unless you are disturbed from the origin, because origin is the equilibrium point. Your origin is the equilibrium point. So unless you are disturbed from there, you will remain there. So after the disturbance, then one has to again see where one is going, whether again coming back to the origin or going further away. That one has to see. Matrix A is a full rank. One cannot say anything certain with certainty about this. Okay.
So why, sir, option D?
Why?
Why option D is incorrect?
See, matrix A is not a full rank, will mean that there is a zero eigenvalue. Okay. So in with this statement, that we are observing from certain parts of the state space system moves towards the origin, this does not negate any possibility of zero eigenvalue. There may be negative eigenvalues of the system which are making it move towards the origin, but if there are other possible like eigenvalues which are positive or zero, so these things can disturb this condition of total convergence from everywhere in the state space. So you actually cannot predict, cannot say anything about all the eigenvalues, right? So you cannot say anything about all the eigenvalues only by observation from certain parts of the state space. If you had observed that from all parts of the state space you are coming to the origin, then you would have for certainty you would have said that all eigenvalues are negative. But now you are unable to say for certainty that all eigenvalues are negative, and when all eigenvalues are may not be negative, then there is possibility that one of the eigenvalue is 0, and when one eigenvalue becomes 0, the matrix will lose its rank because the determinant will be 0.
So, sir, it is possible to have a matrix of full rank?
It is possible, but it is not always so. So suppose that in this case, suppose, so we are only doing the observation from certain parts of the state space, right? So what I am saying, what I am saying is that you are not confident about all the eigenvalues in this particular case, and when you are not confident about all the eigenvalues, you can have an eigenvalue which is 0, and that will make the matrix lose its rank. So the matrix is a full rank, you cannot say it with confidence at this moment. Okay.
Okay, sir.
Okay, let's see. Harsh is still keeping up his hand, whether he has a follow-up question or not.
No, sir. No, sir.
Okay. Inzamam, you have a follow-up question?
Yes, sir.
Yes.
Yes, sir. In this question only, if the system is forced, then sir, option C will be correct.
If the system is forced, I think we were discussing about unforced system. I have not mentioned this specifically here.
No, sir. I am asking.
Yeah.
Suppose sir, the system is forced, then option C will be correct.
And no, actually, how you are forcing it, it will depend on that. So if you are not forcing it properly, then you will move away. Okay. If the system reaches origin, eventually it will remain there. Okay, you are saying that if we have a forced system, then will the option C be correct?
Yes,
that is
sir.
your question.
Yes, sir.
Yes, it can be. It depends on how you are designing or forcing function, which is the control input basically. Depends on how you are designing or controlling. Mostly in such cases, you will see mostly our control input is we will also design a controller which is a very standard, very basic one, the state feedback controller. Most controllers are state feedback controllers. That means they are having a very direct relationship with the states. So when the state becomes 0, the control action will also become 0. So it will not disturb it from the equilibrium point. Okay, Inzamam? Okay,
Yes, sir.
Rahul again has raised his hand. Yeah.
Sir, for quiz 2E, problem 6, we are saying that for a non-linear SPR,
Hmm.
origin is not an equilibrium point.
Yeah.
Why, sir?
Origin may not be an equilibrium point. It can be an equilibrium point. It may not be also an equilibrium point. This you will understand when we talk about nonlinear systems in details. However, I think in the lecture videos I had mentioned this once. That's why I kept this question.
So we are talking about unforced system.
Yeah, it can be. So you take any some nonlinear system, you take x square minus 1. Okay, your x dot equals to x square minus 1. What is the equilibrium point? Plus 1 and minus 1. Okay, those are the equilibrium points. The scalar system.
So, sir, nonlinear systems are not of the form x dot is equal to ax plus b.
No,
Yeah, they have more
no,
powers.
no, they are not of this form. Okay, they are not of this form.
Okay, sir. And sir, for quiz 2E, problem number 1, I had a doubt, sir.
Hmm. Okay, let me see. 2E.
Why is option C incorrect?
Problem number 1.
Yes, sir.
In the context of an unforced, not linear time invariant system in SPR, the range space of the matrix A, is actually a space, the space of velocity vectors. Yes, because it is x dot. What you are getting from Ax, you are getting x dot, which is the velocity vectors. You are not getting the future trajectory. The trajectory is xt. The trajectory is your x basically. It is in the x state space. The trajectory is in the x state space. What do you mean by trajectory? Trajectory means the locus of all the points through which you are traveling, that remains in the x state space. Okay.
Okay, sir.
This sort of finer differences are there in definition, so you have to take care of these things. Okay, so
But sir,
Rahul,
we can say that the dimensions of both will be same now. Dimensions of velocity vector and dimension of future trajectory.
yes, that you can say, that you can say, yes. Dawar has raised his hand for a long time, so let's first hear out Dawar Hussain and then I will come to Kushi. Yes.
Yes, sir. I was having a doubt in quiz 2F, question
2F,
number 4.
2F, question number 4.
Sir,
Suppose it is observed that no matter from where one starts in the state space, system move towards the origin for an LTI system. A very good
how can
condition. Okay,
how
so
can
what
LTI system behave like this? Sir, my doubt is
what?
that how can how can linear time invariant system behave like that it is going to origin from
Yes,
everywhere?
yes. So you think about unforced system here. So I think we were talking about unforced system in this case. It's not mentioned here explicitly though. So you all the eigenvalues are negative. If there is a system where all the eigenvalues are negative, so actually this is the conclusion here. Then what will happen? No matter where you start, your velocity vector, which is basically a composition of these modes, which are there, modes of motion along the eigenvectors. So that is the direction of the velocities. So always the velocities will be pointing towards the origin. So no matter where you are in the state space, you are your velocity is pushing to you towards the origin. So that is the case when this sort of thing will happen, and most of the systems you will encounter in practice are inherently stable in nature. These are stable systems actually when you come to the origin, no matter how. So inherently they are stable systems. So if you don't give any external input, they will eventually die down, their response will die down and everything will come to zero. Otherwise kya hota, what will happen otherwise? If there is an unforced system and you are always getting an output from there, what law would it violate? There is a fundamental law of physics that it would violate. It would create energy out of nowhere, right?
Yeah, yeah.
So that is the situation. So uh, so all eigenvalues of the system are negative. The system may eventually move away from the origin. This will not happen. This will not happen because you are always going towards the origin. The system will reach origin, eventually remain there. This is also true. Matrix is full rank now because you are confident about all the eigenvalues being negative. Okay, all the eigenvalues being negative, so there is no eigenvalue which is 0, so there is no fear of losing rank. Okay, in this case, and since all the eigenvalues are negative, you will not be able to have determinant 0. Okay, Harsh again has raised his hand, but I will come to him later. Khushi, you say first. So in the
Yes,
meantime, Vikram has posed some question here. I will see. Okay, Khushi.
yes, so sir, I was talking about the question, quiz 2F, a fifth question in which it is given like if it will reach the origin and will remain there, C option.
Hmm.
So, sir, in this question, it is not mentioned that it is whether it is an unforced system or a forced system. So we will not like mark this option because it is not certain that if it will reach there. Because if there is some force like on the system, so it will eventually move from there, and all the values are not -1. So it will like go in some other direction if like eigenvalue is not
Yes. So
-1.
actually, I will take the responsibility of not framing this question properly, but I meant unforced system while I was framing this question. So in that purview, probably you would understand why these answers which have been marked correct are actually correct. But in future, I should actually mention that I am asking for an unforced system.
So, but if it is a general system, so I think so we shouldn't mark this option. Like
If
if it is
if
like
it is a general system, then you will not be certain.
yeah,
So it will depend on your control input actually.
yes.
Okay, but normally our control inputs are designed in such a way that we are when we come to the equilibrium point, we don't disturb it from there. So the control inputs will also die down when we come to the equilibrium point. Okay, in normal cases, like standard in traditional controllers are like that only. So it will not disturb it from the origin. So, if you have made a controller which takes it to the origin and then it takes it away from the origin, then you have not made a good controller. Okay.
Okay, sir. Okay,
Hmm.
thank you, sir.
Hmm. Harsh.
Sir, in the previous question, which Rahul was asking about the space of velocity vector and the space of future trajectory.
Hmm.
So, in that, if we are given the space of velocity vector like any two-dimensional or three-dimensional space,
Hmm.
so we will not leave that space because the system is unforced. So, future trajectory should also be confined to that space only.
Oh, okay, okay. The confusion here is one is the space of position. So one is a space of positions or the actual state values. Another is a space of their derivatives. So since the quantity has changed, so one is the space of the coordinates, another is the space of the derivative of these coordinates. Though they are of the same dimension, they are not the same space. Okay, they are of the same dimension, but quantity wise, physical quantity wise, they are not the same physical quantities. So they exist in different spaces, so we can separate their space out. However, when we look at their space, look at the coordinate space, which is a state space, and we look at the velocity space, even though they are different, we would see them both as three-dimensional or four-dimensional spaces having their elements coming from the real number field, real field. Okay, so it might appear to us that they are the same, but it is not. They are not the same. They are different because their actual physical quantities that they are trying to represent are different. That is why they are different. So this is the reason. So this is a more abstract sort of a thing. So you need to grasp it in that way. So they are not in the no, they are not overlapped. So otherwise, what would happen? Whatever is three dimensional will all be in the same space, but that is not what happens actually. Okay, so all the different quantities will have the different three-dimensional spaces. Different quantities will have the different three-dimensional spaces, although the mathematics in there will be the same, because ultimately when we are doing the maths, we are only crunching numbers. That's all we are doing. But the understanding of the spaces must remain separate, because we are dealing with very different quantities. Okay, so I guess I can now go to Vikram's query. He has given some, I don't know if this will open here, captured photo. This is also not very straightforward. R1 AB, R2 CD. Vikram, can you explain what you have tried to say here? Can you
I
put
was
it?
trying like if rows are independent, then for same dimension matrix, column will be independent. So I take example of 2 cross 2 dimension matrix, and then I take A, B, C, D, 4 elements in it. Then I take rows are independent. So this is a line segment in a 2D plane. If you see correctly, then these first line will not be a multiple of those other points. A comma B will not be equal to alpha C comma D. So A comma B will be some quantity A1 into C1, and similarly B will be B1 into D, some integers. So now A1 and B1 must not be equal. So this will be the condition for them to be independent. Then using this condition, I proved that the columns will be independent. So this was my conclusion.
Yeah, okay. Consider A is A1C and B is B1D. A1 not equal to B1. Yes. Then C A11. C A11 is the column, will not be equal to D B11. Yes. Yeah, your proof seems to be good. So good. But there is this is for the square matrix, which we already had a conclusion that independent rows will mean independent columns. But what about that thing about tall matrices? So when there are tall matrices, that means number of rows are more than the number of columns. Then obviously we cannot have independent rows. That is one thing for certain. But whether the columns will be independent or not, is there any doubt here that the columns can remain independent, even though some rows can be dependent? So let me share the screen quickly and give you some example like on this. So we need some rows to be dependent and columns will be independent. Purely this is one example. So if you have a matrix like this where the rows are more than the number of columns, you cannot say for guarantee that the columns will be independent. Also, you cannot say with guarantee that the columns will be dependent. Okay. So here in this particular case, the columns are independent. However, you can have this case also where the rows are dependent as well as the columns are dependent. So when rows are more than number of columns, then obviously this will imply one thing, that rows are dependent, but this will not imply anything about columns being dependent or independent. So you will not be able to conclude anything from this, and that is the reason why you will not be able to conclude about the triviality or non-triviality of the null space. Okay. So I hope this is clear. Okay, so today there was a very good discussion. Thanks to all of you for participating, and never fear to ask me questions, because sometimes I also do mistakes while framing some question, and especially when I am doing some quizzes and all. One or two mistakes there can be possible. So when you are in doubt, when you are in confusion, it is always better to clarify things, and this will also help me correct myself in future. Okay, I think if there are no further queries, we can close the session here, because there is only 10 minutes remaining. So I guess it is fine. So we can close the session and see you again. Yeah, Shivam, you saying something? Shivam?
No, sir, by mistake.
Okay, okay. Okay, fine. So let us close the session now. Thank you for attending.